Now for our inductor, we can do pretty much the same thing. We can use a loop rule again, and our loop rule will give us V source as a function of time minus VL as a function of time equals 0. So we can get VL as a function of time is equal to, right, capital V max cosine of omega t. And then we can also get, again, V max cosine omega t as the voltage of our source. The voltage of the inductor we can also write as L times di of t dt equals 0. And we can solve for di dt. And that's going to be capital V max over L cosine omega t. In order to get to I, we need to take the integral of both sides as opposed to having to take the derivative. And that gets us the current over the inductor as a function of time. V max over L remain unchanged. And the integral of cosine is positive sine omega t. And then we have to divide by omega. So we have another trigonometry rule. And we know, of course, right, that sine and cosine are always going to be off by 90 degrees. And so if positive sine is off by plus pi over 2, sorry, negative sine is off by plus pi over 2, positive sine will be off by cosine of omega t minus pi over 2. So we get that our current of an inductor is equal to our capital V max over omega L cosine of omega t minus pi over 2. So we get the same thing over here, that when voltage is the shared measurement, the voltage over our inductor as a function of time is just capital V max cosine omega t. The current as a function of time is going to be capital V max over omega L times cosine of omega t minus pi over 2. But then we also want to consider, right, what happens when the current is the shared measurement. So when our current is the shared measurement, we're going to continue with this, right, current, L as a function of time, is equal to the maximum current. And then cosine, we are going to say, right, the phase of the current is 0, cosine omega t. So then our voltage over the inductor as a function of time. To get from V max to I max, we have to multiply by omega L. And then we have cosine of omega t. This was minus, so now this is going to be 90 degrees ahead, plus pi over 2. And we can draw our phasor diagram again. So if we have, again, an Imax phasor in the first quadrant, again, the current as a function of time is going to be the x projection because this is going to be omega t. And our voltage is going to be 90 degrees ahead. This is our voltage max. This being omega t plus 90 degrees. And so then our voltage would be the x projection of this vector. So again, we have, right, that current is ahead of voltage for capacitors. Current is behind voltage for inductors. And we can use that either when we have voltage being the shared measurement, these equations, or when current is the shared measurement, these equations, depending on how we want to do that. One last thing, since we have a little bit of time, a little bit of space, we talked about these relationships. So Imax for an inductor is equal to Vmax for an inductor over omega L. And I max for a capacitor was equal to V max for a capacitor times omega C, but we can write it instead as 1 over omega C. And we'll see then that we get reactances like this because we had the I max for a resistor was equal to the maximum voltage for a resistor over R. So these terms, omega L and 1 over omega C, act like a resistance for each of these in that they provide us a relationship between the maximum voltage and the maximum current, the maximum voltage, the maximum current, the maximum voltage, the maximum current. So we can call these the reactances of them. And so we have that X sub C is 1 over omega C, and X sub L is omega L. We'll play around with these a little bit further as we look into more AC circuits.